All right, so in this lesson, we are now actually going to solve for the metric of the Schwarzschild solution to Einstein's field equation. So we are now finally at the point in our work where we can take the most famous equation, well, I shouldn't say the most famous because it's not the most famous equation, but probably the most intellectually significant equation that arguably has ever been captured by science, by human endeavor called science. We can actually attempt a solution of this thing. And we will succeed because we are following in the footsteps of Carl Schwarzschild. But, it's a big deal to know how to do a solution of this thing. First of all, if you can solve this guy, if you can walk through this, it means you've climbed quite a mountain of math to get here. Now, we've already kind of done the setup and things like that, but you've accomplished quite a bit if you've arrived at the ability to solve the Einstein equation, even in this, what is certainly universally considered the simplest circumstance, which is the Schwarzschild metric. But the catalog is exactly a catalog of spacetimes because it could be retitled Book of Each and Every Known Solution of the Einstein Field Equations, right? If you have a solution of this thing, it's such a big deal that we actually catalog it. This isn't like algebra and the quadratic equation where the solutions just come pouring out of a calculator, right? It's the opposite of that. So they keep track of every solution that's out there. Like we studied the Ernst solution, which I don't know much about, but even the brief encounter we all had together, it was pretty intriguing, right? Electric fields and black holes. Wow, somebody really put some brain power into that thing. Anyway, so now we are going to begin. It's going to take 2 lessons to get through the whole thing, but it's totally worth it. So let's go. All right, so let's look at the setup again, just to remind ourselves where we're starting from. We've got our spherically symmetric metric set up, right? I haven't changed this yet, but I don't like the way I wrote that, so I'm going to change that in the book. But this is the Schwarzschild coordinate system where remember, areas on spheres at radial coordinates are all as they would be in Euclidean space. And we've decided that we are going to have these possibly time-dependent expressions for these 2 unknown functions. Everything boils down to these 2 unknown functions. If we can nail those down, we're done. That's the solution. Now, we're going to discover that time dependence is actually impossible in the situation we've proposed. So we're going to discover that the solution is, in fact, static. So if this thing is going to be spherically symmetric for all time, then it's got to be not a function of time at all. And we're going to show why that's the case. We've boiled this down to the Einstein equation in empty space without a cosmological constant, which is r mu nu equals 0. So that is the Einstein equation right here. And we're only working in the exterior of some super simple mass distribution. Now, this point is where we're going to start. We're actually going to start with this conversation about the exterior because ultimately these are differential equations, so we need boundary conditions. So one of the boundary conditions for this is going to be that way far away from this mass, we expect space out here to be flat, right? If you're very, very, very far from the mass, it's like the mass isn't there at all, and whatever solution we get for G mu nu, it better be Minkowski spherical at large values of rho, very, very large values of rho. Or there should be a value of rho that is so big that whatever expression we get for G mu nu of R and T, presumably, right? It's a function of all 4 coordinates. I don't know why I'm just nailing that down. T, rho, theta, and phi, right? This tensor that's at every point in space given by these coordinates, there should be a value of rho so big that it ends up being Minkowski flat spacetime, right? Just like the Minkowski spherically symmetric version, or the spherical coordinate version of the Minkowski metric that we talked about in the last class. So that's actually a boundary condition, because that's a condition on this thing at large values of rho. And likewise, there needs to be some kind of discussion about what happens at small values of rho, right? I mean, small values of rho are very close to the surface, very close to the surface of the of our mass, right? So right in here. So that's an issue, isn't it? The interior solution, right? So presumably if there's an exterior solution, there's an interior solution. The interior solution for the Schwarzschild metric, we're not solving for that. But presumably the interior solution will give us a G mu nu in here. And then there will be a G mu nu from the exterior solution. And for this to all work, we're going to have to match the boundary condition right here on the edge of the matter, right? In other words, these solutions are going to have to agree with these solutions for rho, for the radial position of the sphere. So that's going to be something tricky. It turns out that in our solution, we're not going to have to worry about that, because we can, for the purpose of what we're doing, we can assume that this guy is really, really, really small. And we can always kind of push off dealing with that boundary condition forever, right? Just allowing this infinitely tiny bit of matter that is infinitely dense. Remember, this is a classical theory. So we could postulate sort of unlimited amounts of density, and we can go to unlimited small distances. So we'll think a little bit more about this boundary condition later, but it actually turns out that it's not a big problem. But the exterior one, the one for being flat in the distance, that is very, very important. So that is the setup. Let me undo my... so that's the setup. Reminder on that's the setup. And now we've got everything we need to go through this really difficult program of starting. What we're going to do is we're going to start from the metric, right? This metric with these ambiguous parts. We're going to produce the connection. From the connection, we are going to produce the curvature tensor. From that, we're going to produce the Ricci tensor. And from the Ricci tensor, we're going to just create that equation. And in the end, we're going to have differential equations for A and B that we better be able to solve. At this point, this is a bit anticlimactic. And let me take the time to say that that is a great way of gauging your learning. In my experience, there are very few things that I've desperately wanted to be able to understand and desperately wanted to be able to do, that by the time I understood them or were able to do the things, I didn't get this feeling of anti-climax, or I had moved on to desperately wanting to know other things that were more advanced. So, for example, understanding the mathematics of a black hole, if you learn the mathematics of a black hole and you're still flabbergasted and amazed and you think it's so cool that you've understood it, you probably don't understand it, because by the time you go through all of this hard work to get to the point where you really understand a black hole, it's no longer all that impressive, right? That's sort of the irony of learning something new, is by the time you're qualified to understand something new, it is ironically less amazing by its very nature. You've beaten out all of the fantastic, amazing beauty of it. And it isn't until you've understood it for a while, step back a bit and look back and say, hey, that journey from not knowing to knowing was pretty fun, right? It was pretty fun. When you're right here and you hit it, it's kind of anticlimactic. But when you stand away and you look at what you've done, you realize the full arc you've gone on from not understanding to understanding, then you suddenly are like, oh, that was a really great thing. I'm glad I did that. And it was a big accomplishment to get to the point of learning this thing. But now I'm kind of interested in something else. I want to learn about the interior solution or I don't know, any other thing out there. Your mind is usually somewhere else. This is really true in music. I'm going to try to do a series of lectures on music and the mathematics and physics of music at some nearby point. And if you've ever learned to play an instrument and you've wanted to learn some amazing solo or some amazing piece of music, by the time you have practiced enough to learn it the way you want it, it's a lot less amazing at that point. You're almost sick of it at that point. And it isn't even, it's just this sad irony. But the point I'm trying to make here is if you feel this anticlimactic moment, you've accomplished something. And that might be a way to recover being amazed at what you've done, because the fact that it's anticlimactic kind of means you've captured it. And you should be alert to the fact, if you learn something and it's not a bit anticlimactic, you may want to double check to see if you really have captured it all. Anyway, little philosophical life lesson there. So let's now see, why is this a big anticlimactic exercise? So let's go to, we talked about these things. This is that starting screen, right? We want to calculate the Christoffel symbols, right? Here's how Christoffel symbols are calculated. And in our lessons in the past, we've gone through exactly how to do this and why this is the case. Why, when you have a metric, you're forced to have a metric connection, which we call the Levi-Civita connection. And in coordinate basis, the Levi-Civita connection's components in a given coordinate basis is the Christoffel symbol. So this is an expression that is something you should know at this point. But in order to calculate this, you need to calculate these guys. You need to know the derivative of the metric component Rj with respect to k. So every R, every j, and every k possible, we need to be able to calculate these derivatives. And, well, we know the metric. I better move that over here. Hold on. Here it is, right? This is the metric. So this is g mu nu. And, some of the metric components are fully known. These two are fully known. They will never change. These guys, these guys will never change either, but we don't know what a and b is. But we know enough about the metric that we can actually take those derivatives. Meaning we can take this derivative, this derivative, this derivative, and this derivative. Now, there are two kinds of derivatives. There's derivatives with respect to time, and there's derivatives with respect to rho. The reason there's only, there's four possible derivatives, right? There's derivatives with respect to theta and phi. As far as a and b are concerned, only two matter. The ones with respect to time and rho, because we assumed, we didn't assume. We showed that a spherically symmetric metric can only have those two dependencies, rho and t. They can't have theta and phi dependencies. So I will, if I'm talking about dA d rho, I'm going to write that as a, I think, prime. Yeah, see, a prime. And dA dt will be a dot. So the dots are partial derivatives with respect to time. The primes are partial derivatives with respect to rho. And there's no requirement for a symbol for partial derivatives with respect to theta or phi, because the only things that are functions of theta and phi, the only metric components that are functions of theta and phi, don't have a and b in it, so we just execute those derivatives. So, for example, g mu nu with respect to theta, this entry here, the way this chart is designed, this should be g phi phi derivative with respect to theta. Well, what was g phi phi? Well, that was rho squared sine squared theta. That equaled g phi phi. So g phi phi equals that. So the derivative of this with respect to theta is it's obviously the derivative of this with respect to theta is simply 2 rho squared sine theta cosine theta, right? I mean, that's what this table is telling us. Yeah, so I guess to read this table, the mu and nu are for example, this one. The mu and nu are replaced by, mu is replaced by t, nu is replaced by, mu is replaced by this column, or no, it should be row column, so it's row column, but it doesn't really matter since it's symmetrical anyway. It's a symmetric matrix. So this is the entry for the derivative of the phi term, right? So phi term theta, that's this guy. That's how to read that table. Likewise, there's no metric element that has any dependence on phi. So they're all zero. They're all zero. These lines are zeros because they look better that way. But for example, GTT, the derivative of GTT with respect to t, that's what this entry would be, right? That's the t for the replacing the mu nu, and there's the derivative. This whole chart is the derivative with respect to t. But we know that GTT is equal to minus a. I think we called it minus a. So the derivative of minus a with respect to t is given by a dot. So there it is, a dot. Likewise, b dot, and then you have a prime and b prime for the spatial derivative. Right? So it's pretty much that simple. And so now we can calculate all the derivatives of the metric. And notice these aren't, it makes no sense to say that these are regular partial derivatives, which you can tell because I'm using a single line here, right? So G mu nu single line kappa is del kappa G mu nu, right? That's the definition of that symbol. But we've been doing that forever. Okay, so once I can calculate all the derivatives, I can now calculate all of the Christoffel symbols, right? I just plug in the appropriate derivatives right here. So for example, if I want to calculate 0, 0, 0, I calculate 1/2 G0 R, and then GR 0 partial 0 plus R 0 partial 0, that's the same one, right? Yeah, I guess that makes sense. Minus G 0, 0 partial R, right? So I can now calculate this 0, 0 term just by doing this. And I know all these things, right? I get these three off the table, right? The G 0, 0 partial 0 term would be the time term, partial time term, which is this minus a dot, right? So this is actually not 0, comes in as a factor of 2, which will cancel that 2. But I have to multiply it by, the only term here that can survive is the on-diagonal terms, right? The off-diagonal terms are 0 to begin with, so their derivatives are 0. So R has to be 0. So I have to multiply this by the inverse of G00, 0, which is minus 1 over A. So that'll be interesting. And this guy here, G00, 0 with respect to R, the only term there that can survive is when R equals 0. Remember, R has to always be 0, actually, because this will be 0 if R is off. And that would be because this is symmetric too, right? So R has to be 0. You know what? I just write it out, right? I mean, it reduces ridiculously much, right? These two cancel, right? These two cancel. Let me see, cancel like that. And so you get this equals 1/2 times minus 1 over A times minus A dot, which equals 1/2 A dot over A. So that's what we're going to do. We're going to do what I just did for every possible connection coefficients, and we keep track of the ones that don't turn out to be zero. Some of them are likely to turn out to be zero. So I just did one of those calculations here, but you could see how we would do the same thing for any other one. I'll pick another arbitrary choice. I'm not going to use the zeros. I'm going to use, just to make it a little clearer, I'm going to go with t. The indexes will be, say this case would have been t, 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 right? I'm going to stick with that for right now because we're calculating individual components, right? So say I wanted t, I'm just going to pick one at random, t theta rho, right? So t theta rho, okay, that would be this expression, right? The G00, it has to be that one term because all the others are off diagonal. So the zero here comes from the t. See, I promised I wouldn't use, hold on. Okay, I replaced the zeros with t. So, but the point is, look, that's off diagonal, that's off diagonal, that's off diagonal. So all three of those are zero. So this guy is zero. So we do this for every single connection coefficient. When we calculate each one using these expressions here. And what is the result? Well, here's the result. The result is this table. So let's look at this example, right? All the connection coefficients that have the form T0 mu nu, where mu nu is each of these possibilities, we've calculated. Here's the one we did together. And here's the other one. Here's the other two that are not zero. All the rest of them are zero. So you get T0 rho rho, and you get T0 T rho, right? So there you have it. There you have the three connection coefficients that have the superscripting of zero. And then here you have the one for the superscript being 2. You get all of these guys being 0. You get 1 over rho for this one for whatever reason. And you get minus sine theta, cosine theta, right? You can almost see why, right? Here I've actually written what the expression looks like that you have to calculate. And obviously that's 0 and that's 0. So you have phi del theta. Well, remember the phi term here is sine squared theta. So you get this. And then you have the 1/2 that cancels the 2 that hung out in front. And then G theta theta up is 1 over r squared. So you lose the 1 over r squared. So back here, when we looked at this term here, that 2 is canceled by the 1/2, and the rho squared is canceled by the G theta theta, which equals 1 over rho squared, right? So that's pretty easy to see how that connection coefficient gets calculated, right? This one here, that is. And then over here, the gamma 1, the superscript 1 Christoffel symbols, those are looking very similar to these, but there seems to be two more of them down here. There's no pattern, by the way. I mean, when you're calculating it, you feel like, oh, I got a pattern going, but it never seems to hold out. There's always something. And this is spherical spacetime, so you still have like a cotangent here for this, the T phi, right? When I say T3, this is actually a mix of symbols. I should probably have written this T phi mu nu. Since I'm replacing everything, well, I'm using mu nu here, and those are supposed to be numbers. So understand it's T phi mu nu. I think that's clear the way it is. But here and here are the two non-zero versions of it. So we've calculated every Christoffel symbol for the spacetime. And all the Christoffel symbols, the important thing to take away here is that the Christoffel symbols are in terms of our functions, our mysterious unknown functions A and B, right? A and B. We're still trying to figure out what those guys are, right? And they show up in most of the Christoffel symbols, not all of them, right? They don't show up in every Christoffel symbol, but they show up in the ones I've circled in red. So we're still trying to get at those, but at least we've got, I it's no big deal. If you have the metric, you can take the derivatives in terms of these unknown functions. You can add them together in these combinations. We haven't made that much progress, but we've done a lot of calculating. So what would we do next? Well, if you have the Christoffel symbols, our goal is to now calculate the curvature, because we're trying to get at RAB equals 0. So I need RAB. So far, I'm only at the Christoffel symbols. So I need to calculate the curvature tensor, right? And the curvature tensor is calculated by this formula, right? Which we studied extensively. If you have a connection, you have a curvature. And in this case, our connection is the metric connection, and we know these Christoffel symbols, right? So here's two Christoffel symbols multiplied together, but in this case, the Christoffel symbols come in as their first derivatives. So we can take every component of the curvature tensor and we can calculate the last two pieces, because we just have to multiply together these guys, right? The guys we found here, right? All of them, including these guys down here. At various products of these guys, when both the first one and the second one happen to not be 0, there's a value there, and we can calculate those. These, however, we've got to take derivatives. So now I've got to take the derivatives of all of the Christoffel symbol terms. And so I created this chart, right? The t derivative of the 0 tt term, the rho derivative of the 0 rho term. That's this thing, right? And this is just derivatives of these expressions here. So let's try an example, right? So let's take the let's take this term here, the t00, the gamma t sub tt term. So that's a dot over 2a, right? So we go over here, we write a dot divided by 2a, right? So that is equal to gamma 0, 0, 0. So now I'm interested in this with respect to, say, let's just go with respect to 0, right? With respect to 0. Well, what's the derivative of this thing with respect to 0? That would be the partial derivative with respect to the time variable of a dot over 2a. And so I don't bore you, I'll just write it down. And here it is, right? It's this expression. That's a double dot on a. That's an intentional double dot on a, single dot there, 2a squared in the denominator. That should be the entry on the table representing gamma t, right? Because 0 is t, which is this guy here. It's that row, it's that column, and this is what I wrote here. And that just looks like the same thing over a common denominator of a. So that's how you calculate this derivative, right? And now you have to do this for every single one of these terms. You have to calculate every single partial derivative of gamma with respect to a dot, a prime, or t. Well, you've got to calculate every derivative of every Christoffel symbol with respect to every variable. And the good news is a lot of them come out to be 0. A lot of them won't be obviously 0. They will be 0 after a lot of cancellation. Some will be 0 just because the Christoffel symbol itself is 0, right? So some of them are very easy. Some of them are a mess, but you've got to do every single one. Let's see, which is the most complicated one here, just out of curiosity? Which is the sort of the most unusual one? You know, when you start having these phi-phis, you start getting the sine thetas in there. That's cool. So those are kind of tricky. But all of the rest are just combinations of a dot, b dot. This one's fun because it's got a dot, which is the partial of a, but then a prime. So we're lucky that we can reverse that, because that's really partial with respect to t, partial with respect to rho of a, right? That's what this thing is. And you can reorder partials in these things. That's sort of a famous calculus fact. Likewise, that shows up there. And then you get some double primes here, you get some double row derivatives. But anyway, in the end, we have to calculate every single one of those things. And then once we have all of those things, then we are able to calculate the curvature tensor of the spacetime. And the curvature tensor will be solved in terms of our unknown variables A and B. I shouldn't say variables, our unknown functions A and B. So let's see what that looks like. Well, this whole process is just grossly brute force, right? So we go back to our brute force definition of the Riemann curvature tensor, right? And we've been looking at this before. So now I need to write this expression down for each and every component of the Riemann curvature tensor. So I'm going to do this for just one example because I actually kind of like doing this. So the example I'm going to use is RT rho t rho, RT rho t rho. It's one that has a real substantive result, so it's not trivially zero. A lot of them are. But rho t rho, let me make sure. It's also, just to avoid any confusion, the correspondence between the variable, the coordinate letter names and the coordinate numbers are t is 0, rho is 1. So this is rho 0, 1, 0, 1. But I'm going to stick with this format. But taking this equation here, the definition, and applying it to this particular component of the Riemann curvature tensor, this is the formula that will give us this component. So we have the two Christoffel symbols with the two Christoffel symbol derivatives, and then these two Einstein summed straight up Christoffel symbols. And because now we have our table, right? We have our table of, oops, that's the result. I'll show you that in a moment. But we have our table of derivatives. We'll be using these two mostly. The derivatives with respect to the Christoffel symbol with the upper index is time, and the Christoffel symbol with the upper index is radius. I should change these tables so that one is a row. If I'm going to use rho and theta and t in the columns and the rows in the columns, I should label that table the same way. I think I want to keep the numbers because that's the way the Einstein sum kind of is best understood, indexing from 0 to 1. But you can index from t, rho, theta, and sigma. You just got to know each coordinate. You're going to sum over all the coordinates. So these are the two tables. So we got these derivatives, and over here we have the actual values of the Christoffel symbols themselves. So all the calculations we've done are now setting us up to do this calculation. So I will immediately make these substitutions. And here you have it. The substitution is, this first substitution is just blowing up these Einstein sums, right? So where we see epsilons of this Einstein sum. So here, where we see epsilon summing with epsilon in these two cases, I blew those up to the ones that survive. The only ones that survive are the TT term for this first one. The ones that survive is the TT term and the rho term. And for this one, the ones that survive, likewise, it's T, T, and rho. And you can see that because if we go back to the actual table of Christoffel symbols, here you see overwhelmingly the theta and the phi, almost all of them are 0. And the ones that aren't 0 involve phi or theta in the subscripts, right? But in our case, the subscripts of these guys, when you work it all out, there's never phi or theta down here. So these guys are all going to be 0 unless you're summing over t or rho. It's just enumerating, right? You could write it all out and then just cross them off as being 0 later. So once we've established what the terms are, now we hunt and peck and we take each term from our table and put it in this expression. And what a pain in the butt, right? But it is something we can do. So each one of these expressions we're going to have to calculate and or go to the table. We've already done the calculation. Now we're just sort of going to the table and plugging it in. I guess the way to say it is now we're calculating this. We've already calculated everything we need. And that's what I mean by this brute force. We're calculating in order to do more calculations in order to do more calculations. So each of these terms I put in here, this first term and the second term clearly come from the table of the derivatives. So for example, this t rho t partial rho, that would come from, this is the t table, here's rho t partial with rho, so a double prime minus a prime squared over 2a squared. That expression shows up right here, right? So I did that for every one of these. And for these guys, same thing. Remember, this is a product of two, right? This is added, subtracted. This is multiplied and then added, multiplied, then added, multiplied, and then subtracted, multiplied, and then subtracted. So that's done. Really, you're done. This expression is the Riemann curvature tensor t rho component in terms of our unknown functions, right? So it's all that part's actually already done, but you can simplify it. And that simplification I did here. First, I just broke it down into. I broke off these differences because you can divide some of them through by a. You can cancel an a in some and not in others. So every place I could cancel an a, I did. And then I just combined like terms, right? And you end up with this expression here. And this expression here is what should show up on a table I made of all of these values, right? I made a table for I made a table for the Christoffel symbols. We made a table for the derivatives of the partial derivatives of the Christoffel symbol. And now using this calculation, we can make a table of all the possible values or all the non-zero values of the Riemann curvature tensor. And that table is right here. This is that table. And here, for example, the one we just calculated. It's the first one on the table. So this is one we calculated. We get this one for free by taking the negative of this whole thing, and that's due to the symmetry of the Riemann tensor. The mixed form of the Riemann tensor is symmetric in these last two indices, or anti-symmetric in the last two indices. And this is the answer we just calculated. We just derived this answer. I think there's a bit of a switching over negative signs or something compared to this, but that is how it's done. So that whole process we just went through, you have to go through for each and every Christoffel's, each and every possible Riemann tensor component. And these are the different answers that you get. How many are non-zero? There's plenty of them that are non-zero, right? Each one comes with a buddy, right, because of the symmetry. But so most of these curvature tensors are actually, well, all the ones here are actually non-zero. That's a lot of them. Yeah, actually, this is pretty cool. I love this stuff, It's so tempting to say, if I look at this carefully, I can see patterns in the tensor, look at these things and I can interpret this as, the twisting, turning of this and that. And, it's just, that's kind of a waste of time, right? I suppose if you were like the master of a certain space-time, like if you were Mr. Ernst, right? Remember from the Ernst space-time of the last lesson? Not that it's important, but if that guy probably really knew the ins and outs of his space-time, the Kerr space-time is totally cool to understand, and it is really fun to see the Kerr space-time. But this looks bad, and this is spherical symmetry. Kerr symmetry is got even more components, right? For example, if you looked at the catalog, why don't we do this? Let's go to the catalog and look at the curvature components as they're presented in the catalog. So here is the curvature components presented in the catalog. This is all from the last lesson, all this stuff. And actually, you see there's much fewer in number here, right? And there's a couple of reasons for that. One is that the fully contravariant or fully covariant form has more symmetries. So from these, you can derive all of the ones that that we've derived. The reason ours are going to be a little different is in order to raise this first index, in order to raise t, you're going to be multiplying by g. In this case, for example, if I wanted to raise t, it would be like gtt here. I'd have to multiply by gtt. And so that's going to add other factors in there. Of course, this doesn't have a and b either, right? So when we solve for a and b, and we substitute back into this whole thing with our answer, there's going to be some simplifications and duplications, and other things may actually be zero. So I guess I prematurely jumped over here. So in the end, there turns out that there's only 6 independent Riemann tensor components. And that's good, because the spherical spacetime, we're hoping we have a high degree of symmetry there. And that the definition of a high degree of symmetry is that, things like this do get reduced from the possible 4 times 4 times 4 times 4 to some much lower number. We should let's compare it though with the Kerr spacetime. How about we do that, right? Okay, I just looked in the catalog for the Kerr spacetime, and what I noticed is they don't even have this section in the Kerr. In the section on the Kerr spacetime, they don't list all the Riemann tensors, and I think it's because it's just too bulky. It turns out, from what I can tell, there are 13 different components. So there's twice as many plus 1 for the Riemann tensor of the Kerr rotating black hole. The difference being that is axially symmetric, and this is spherically symmetric. So the axial symmetry is more than twice as many independent components here. But I digress. We'll get back to all that later. Let's get back to the calculation. So now that we're presuming that you complete all this work, right? And you go through all of the information we have about the Christoffel symbols, and you calculate every single one of these components of the Riemann tensor. And now, we've still got to keep going, right? Just because we've gotten a form of mu, which gave us the connection, which gives us the connection's derivatives, which gives us ultimately the Riemann tensor, R, alpha, beta, gamma, delta. Now we do this to calculate all of the Ricci tensor components, right? So the Ricci tensor components they're much easier. The expression is obvious, right? R alpha beta is simply R alpha. Well, I shouldn't say alpha. R delta alpha delta beta, right? We're just contracting. So we execute the contraction for all of these different terms. And that would involve basically creating the sum, right? This is going to be the sum of 4 different terms here. We can actually kind of look at this. Let's do this first one. The first one that's more complicated. It's a little longer. But all right, let's do this one. Let's do this one here, because it's got 3 terms and it looks fun. So these 3 terms, I need R. So obviously the contraction for that is going to be, this is the expression for the contraction, right? It's going to be R theta theta. We're going to have contract over T, rho, theta, and phi, okay? So what is this? R, T, theta, T, phi. Well, we look over here. R, T, theta, theta, T, theta, right? Yeah, theta, T, theta. So there it is. R, T, theta, T, theta. We don't have to swap it with a minus sign because it shows up in this first column. And it's minus rho A prime 2AB. Let's see if that's what shows up here. Minus rho A prime 2AB. So that term there is this guy right here. So I could say this guy right here is that guy right there. So how about the next one? R rho theta. So I go over here, R rho theta. It's this one right here. Rho B prime over 2B squared. rho b prime over 2b squared is right there. So that one's good too. So I'll circle that. So I know it's this guy right here. And now I need r theta, 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 theta. It's a lot of thetas. Is that one even non-zero? I don't think so. Yeah, see, so there is no r theta, 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 theta. So that one is 0. So we cross that one off, 0. And now I want r phi theta, phi theta. And that better be 1 minus b. R phi theta, phi theta. And there it is, 1 minus b. So that goes there. And there's not much simplifying to be done, because I guess that's in relatively lower terms or whatever. So you do this for each of those, and now you have all the possible expressions for the Ricci tensor components. And here I've included the 0 ones, the ones that are 0. The important point, of course, is they're still in terms of the unknown functions a and b. And as a reminder, a is a function of rho and time, and b is a function of rho and time. So now I think we're at the end. We finally climbed this mountain, right? The mountain started here at the metric, and it ends right here. And the reason it ends right here is because now we have our physics, because we know that r mu nu equals 0. So every one of these has to equal 0, which means I've got a differential equation for a and b in each instance. This one equals 0, that one equals 0, this one equals 0, and let me erase all this stuff. And I can write this one equals 0, and likewise here, this guy equals 0. And each of those is a differential equation, right? This is a differential equation right here. And it's coupled because these are all have to be simultaneously satisfied. There's some function a and b that simultaneously satisfies all of these differential equations. And so so that makes it a mess. But what really makes it a mess, and now you can kind of see the issue of nonlinearity, right? The Einstein equations are nonlinear in the metric just straight up. I mean, if you blew this up in terms of just the pure metric, you would see all kinds of nonlinearity. But you still see it here, right? Because here you have b prime squared, right? Boom, that existence of that in this coupled system makes this whole thing nonlinear. Here's a prime squared. This is b dot squared. Here's a prime squared. A prime times b prime, that's a problem. Just b squared itself is a problem. You can't have that in b linear. So this is a massively nonlinear thing, and now it's totally self-evident. So we're stuck with this. We've got to solve these 4 differential equations. Or 5, right? 1, 2, 3, 4, 5. So, and if we solve them for a and b, then we have our answer. And then once we have our answer, we can plug them back into the metric and reconstruct the metric. So how do we attack these differential equations? Well, one thing I should say before we move on is this expression for the Einstein equation, we could have climbed the mountain one step higher, right? We could have calculated r also. We could have taken these components here and fully contracted them to calculate the curvature scalar. And then instead of saying this, we could have said g mu nu equals 0, which would have been r mu nu minus 1/2 r equals 0. And I've seen a proof done this way where for some reason they didn't just immediately set r equal to 0. They felt the need to keep r in there. So they climb one step higher on the mountain, right? Well, this step higher on the mountain. But they don't set this to be 0, and they solve this directly. They end up, of course, in the same place. So it is interesting that assuming making this assumption here, well, the fact that this, well, let's see, the fact that this is true and the fact that r is related to this by contraction, it makes perfect sense, I suppose, because if r is actually 0, its full contraction is going to be 0 too. But there are harder proofs, or not proofs, but harder derivations of the Schwarzschild metric that go from this posture. So all of the expressions that we just set to 0, right? We set that to 0, set that to 0. There is what they set to 0 when they do it their way is this plus 1/2 g mu nu, and then some massive expression for r in terms of a and b. And it still works out, but we're not doing it that way. I'm doing it kind of the hard way, I think, but that's an even harder way, I guess. Okay, just a point in case you look for other proofs and you see that. I haven't worked out exactly how the two analyses would be the same up to this point, and I haven't actually compared the differential equations they get with these and how the process goes from here, but it does end up in the same place. All right, so before we end today's lecture, let's see where do we stand right now. This guy here in the Schwarzschild spacetime, that's what we're calling A rho t. This guy here is what we're calling B rho t. And we've now finally climbed the mountain, and we have differential equations for that. We have a set of coupled nonlinear differential equations that are solved by these two functions. And if we could solve these nonlinear differential equations, we will have A and B. And they better turn out to be these numbers here, right? Because this is the answer, right? This is the answer. So we need to derive these two things using the differential equations we just arrived at the end of this lecture. So at the beginning of the next lecture, I'm going to specify exactly, we're going to rewrite down those equations, and it's all going to be about solving those equations and getting this answer in the end. In fact, why don't I leave this lesson with our final result of all this work. This is the mess. This is the mess we have to weed ourselves through to get to the end. So the end is really just an exercise in solving these. But I mean, this isn't something typical. This isn't regular standard calculus, right? Because these are nonlinear differential equations, right? Which we'll talk about a little bit next time. So, okay, so see